Okay, we now begin part 4.3, which is the crux and really the main part of lecture 1 of alternating current, right? In this week, you have 2 lectures for AC, and 4.3 is really the main part. All right, and this is the root mean square current and average power for the sinusoidal AC. Let's first look at the sinusoidal AC graph. All right. We know that the equation is given by I equals to I naught sine omega t. If we take the square, we get I square equals to I naught square sine omega t. Okay. So there are a few things that you should take note of here. Notice first that the bottom parts of the I square graph is curved like this. There are many cases of students who draw the flipped version, right? They take the bottom of the I curve and just flip it up. So what you get is like a McDonald's sign, right? It's like M, where when they touch 0 is a pointed, that would be wrong. Right? If you do not believe me with your graphic calculator, you can actually try plotting a sine square curve. You should get something with a bottom that is curved. Right? That's something that's important to take note of. Why? Is because sometimes you'll be asked to plot the graph of the power. So P equals I square R. Since R is a constant, the I square R curve graph will look just like this. Right? And students often in the past, we have seen, if we are not reminded, curved that is pointed. Okay. Right, moving on. So let's try to find out what the root mean square current of the sinusoidal current looks like. So first, you square it, you get this. Next, you have to mean it, right? So take the mean. And here it's where you see, or where your mathematical knowledge comes in, right? That the mean value of a sine square curve is just half of the maximum value. And you can see clearly that the area above is equal to the area below the graph, right? So there you go. Right? You cannot imagine how much time it takes to actually do all these animations. Yeah, I'm pretty sure there's some new method now in PowerPoint to do all this. So if you are a PowerPoint expert and you know how to make my life easier, please come and find me, right? To make physics better. Okay, but the point is done, right? The point I'm trying to make is that you have to take the mean by finding the line where the areas above and below the graphs are equal. You're done. And mathematically, that would just be I naught square, the peak value square, divided by 2. Okay. So the next step to find the root mean square current is to take the root. So you square root it. And you realize, right, if you take the square root of I naught square over 2 and you root it, you eventually get I naught over square root 2. So here we arrive at a very powerful and important conclusion, right, of the root mean square current of any sinusoidal current, or sinusoidal AC, is I naught square over square root 2. Right? Yep, so this slide is just to prove to you, how much effort it takes to do this, but this is just for fun. Right, so we get this, right, that the root mean square current is just I naught over square root 2, which approximates to 0.707 I naught. Okay, this also then applies for the alternating voltage, right? That VRMS is V naught over square root 2. Right? I believe you, if you're interested, you can try to work this out yourself. You will get the same values. Next, if you look at the power, since power equals to I square the mean square current times R, or you can take the root mean square current squared times R, right? You essentially get this. If you work it out mathematically, you get I naught squared R in the numerator, and a square of a square root 2 gives you 2. And if you look at the numerator carefully, I naught square R is essentially the peak current square times R, which gives you the peak value, peak power. And this is the peak instantaneous power, right? The highest instantaneous power that you can get. And essentially what it means here is that the average power value of an AC over a whole long period of time is half of the highest power, right, at one point in time. Okay, so we generalize and we get this equation. Okay, so these equations that I've highlighted on page 8 in boxes, right, is very important. But more importantly is that these are only true for sinusoidal waves only, right? Any other waves that's not sinusoidal, you cannot apply these equations. Like for example, in the square waves, you cannot apply these equations. In the triangular or sawtooth waves, you cannot use these equations. Let's see how this is useful. In work example 3, the voltage of an electrical power that we use from the mains is 240 volts, right? So again, you've heard probably many of times that we are drawing 240 volts from the power socket in Singapore. But now you know clearly there's actually 240 volts root mean square value, right? Which means that the peak value should be even higher, right? There you go. So if you're asked to find the peak voltage applying the knowledge that root mean square voltage is V naught, the peak value of the peak voltage over square root 2, you can substitute 240 here and we get 340 volts. Okay. So in this example, I've done two things. I reinforced for you this equation, and I've reminded you what 240 volts from the electrical mains is. It's actually the root mean square value. Okay. Part B, you're asked to calculate the current for an electric kettle with a power rating of 1000. So 1000 is the average power. So you must know where to sub it in. So P is 1000. Root mean square value is 240. The root mean square current is just essentially 1000 divided by 240, and you get 4.2 amperes. Okay? Yeah. Next, example 4. Example 4 was actually inspired by my cousin. He bought something from the United States. Now, in the United States, the voltage from their socket, right, from their power supply is actually 110 volts. Okay, so my cousin bought this instrument. It's actually a air purifier. I think at that period of time there was haze in Singapore, so he bought an air filter or air purifier from the United States, and he plugged it into the wall socket. Right, and I was seated nearby watching TV, and I heard a loud explosion, not explosion, a loud pop, right? I mean, it can't be a pop, it's pretty loud, right? So somewhere between an explosion and a pop, right? And I turned over and I saw smoke coming out of the air purifier. And I asked him what happened. He said, I don't know, this is new, I plugged it in. Then I asked him, where do you get it from? He said, I got it online. And then I looked at him, oh, is this designed for the US? He said, yes. And I said, oh, did it come with a power adapter? He said, no. And I said, oh, then you have wasted your money. I think you just fried the whole circuit. And he said, oh, why? And I okay. And I explained to him what happened, right? So example 4 was inspired by that. Okay, so let's take a look. So a tourist takes an electric water heater, right, designed to operate in the US voltages to Singapore. He plugs it into a 240 volts outlet. The heater breaks down due to overheating. Okay, so let's understand why that happens. Right, so part A, if the heater normally consumes 500 watts of power, normally that means when it's working in the US power socket, what is the resistance of the heating coil? Part B, how much power does it consume during a 240 volts power supply? And part C, what is the root mean square current that flows through when the potential is 240 volts? Part C is just more to practice root mean square current. Okay, so part A, right, using P equals to V square over R, right, we sub in 110 because, right, that is the root mean square voltage in the US. We find that the resistance of the electrical water heater is 24.2 ohms only. Okay. Next, if you plug that in to our 240 volts supply, right, you realize this. P equals to V square over R. I sub in 240 square divided by the resistance that we found in part A. We found the power to be 2380 watts. And if you compare that to the rating of the heater, is only 500 watts. If you send 2380 watts through a 500 watt device, the likelihood is that it will break down, right? It's almost 5 times more than what it's designed for. Okay. So part C, what is the root mean square current that flows? So this is just to practice the math. So it's just Irms equals to V over R. So 240 divided by that, you get 9.9 amperes root mean square value. Right, so the point is this, right? If you have learned this chapter and you listen intently, you will know not to plug in anything without a power adapter, right? That you have bought from the US, right? Or at least you should check the device carefully to make sure it will not have any issues. Now, of course, here comes the other question, right? Because I brought my laptop, right, when I was still studying to the States, right? And I plugged it in, it was fine. I brought it to different countries and it's all fine. Why is it so? We'll learn in the next lecture why this is so. It's because your laptop comes with a power brick that is designed to work with different voltage inputs across many different countries, right? But of course, do read the instruction manual carefully, right? Because just in case your power brick only works for 240 volts, right? Don't just take my word for it. But anyway, after this example, you should save money, right? Yeah, you should be able to save money, and you can say that learning physics help you save some money. So my poor cousin, if he had learned his physics better, he would be able to save a few $100s, right? Next, let's look at work example 5, something a bit more technical. Right, a sinusoidal current described by I equals to 9 sine omega t is flowing in a 12 ohm resistor. We are asked to find parts A to D, which is quite long, the root mean square current I and the voltage V across the resistor, the peak instantaneous power in the resistor, the average power, and then we are asked to sketch the graph. Okay, so part A. We are repeating what we have learned previously, right? Just to consolidate our learning, we know that the root mean square current is the peak current divided by square root 2. And here we need to apply the next knowledge that we've learned in part 2 of this lecture, right? Where the terms. So in the wave 9.0, right? In the sinusoidal wave, you say I equals to I naught sine omega t. So this 9.0 is the I naught. Okay, so you need to match that two ideas together and take this 9 and sub it into this I naught over 2 over here. Then take 9 divided by square root 2, you get 6.4 amperes. Root mean square voltage, again you use V equals IR, that's a little bit easier. Right, since the resistance is 12, the current is 6.4, the root mean square voltage is 76.4 volts. Okay. Part B. Find the maximum power generated. Maximum power generated is I naught square R. Okay, so you sub in the values, so you get 9 square times the resistance 12, you get 972 watts. Average power is P. Average power P is root mean square current squared times R, right? So it's a root mean square current squared times R. We have found that in the previous part at 6.4. So you 6.4 squared times 12, you get 486 volts. I set this example to show you that for a sinusoidal current, the average power is always half of the peak value, right? This is to consolidate the third equation you have on page 8. The third equation on page 8 is P naught over 2. Okay, but again, this equation is only true if it's a sinusoidal waves. Okay, do not apply this for any other waves. Lastly, sketch a graph to show how power varies with time, assuming that omega equals to 100 pi. Okay, so when omega equals to, sorry, let me just finish this, sorry. Power equals to I squared R. If you write out the equation, you sub in I as 9.0 sine omega t squared, you get 972 sine square omega t. Okay, with the graphic calculator, you can actually plot it already, but let me just do it the more traditional way. If you know that omega is 100 pi, omega is 2 pi over t, right? So you have 2 pi over t equals 100 pi now. You rearrange, you find that the period is 2 pi over 100 pi, you get 0.002 seconds. Okay? So if you then draw the graph, you see the following, right? You have a sine square curve. So remember what I said earlier? The bottom is curved and not pointed, right? The peak value is 972, as you have seen earlier here. And you see that something very interesting happens. The period here on the left is the period for the current. It takes 0.02 seconds for it to repeat itself. But if you look at the power curve, it takes half the time to repeat itself. So there were questions that said, sketch the curve of the power for one period. And students sketch one hump, and that would be wrong. Because the period is always defined as the period of the current, which is always 0.02, right, in this case. So you must sketch at least two humps, right, if they ask you to sketch for one period of time. Okay, so that's something that you need to take note of. Okay, so in this example, example number 5, which is a great example, I think, I've done two things. I have reminded you that P equals to average power, P equals to half of the peak power. And second is that I've shown you that one period has 2 cycles of the power. Okay. And of course, the last thing that I wanted to show you and remind you is that the bottom of the curve is bottom of the graph is curved. Okay. With that, we have, and the last one, of course, is that the average power is half of the peak value, so 486. So if you combine what you've learned from part B and C, this is what we get. Okay. So with this, we come to the end of part 4 of this chapter, and we learned these two things, right? First, for direct current, average power is just the max power, which is I naught square over R. We assume that the DC has a constant current of I naught. We learned also this, that for the sinusoidal AC current, the root mean square current is I naught over square root 2, and the mean power is max power divided by 2. And you see this interesting part number 3, yeah, that would be introduced to you after we finish parts 5 and 6. With that, we finished part 4.3. Thank you.